Hello everyone, welcome back to the MOOCs course on Advanced Analytical Techniques. We are discussing the topic Molecular Luminescence Spectroscopy. Myself, Dr. Mohammad Zain Khan, working as Assistant Professor at the Department of Industrial Chemistry, Aligarh Muslim University, Aligarh. Today, I am going to discuss about the effect of various substituents that are present in a molecule on the fluorescence intensity. Let us begin our discussion. So, the effect of substituent groups on the phenomena of fluorescence or on the fluorescence intensity on fluorescence. As you know that fluorescence involve the transition of electron from ground state to excited state, and when these electrons return from the excited state they emit light. If it is happening in the singlet state only, it is fluorescence. If triplet state is involved, it is phosphorescence. So my today's discussion is limited to fluorescence only. So I'm not going to talk about triplet state. So when electrons are excited by absorption of light radiation, of course of shorter wavelength and higher energy, they are promoted to next level. When they come back, they again emit light radiation of longer wavelength and lower energy. So during this process, the molecule which is under study, the substituent present in that molecule has a strong effect or a strong influence on the phenomena of fluorescence, and sometimes these substituents increases the intensity of fluorescence. On the other hand, in some cases these substituent, depending upon their nature, they reduces the intensity of fluorescence. Sometimes I should say they cause quenching. So all electron releasing groups or electron donating groups, as you all know that alkyl groups CH3, C2H5 and group like NH2, they are electron releasing groups or donating group. For example, if they are attached to carbon, if this carbon is attached to a methyl group, then we show arrow towards carbon. This means that this methyl group is further transferring electron towards this particular group. Or if NH2 is attached, it also releases electrons towards the other side. On the other hand, we have certain groups that are called as electron withdrawing groups, like oxygen. It is an electron withdrawing group, so if it is attached like this, it will pull the electron pair towards itself. Or if oxygen is connected to carbon, it pulls its electron. Or if oxygen is connected to carbon, it will pull the electrons towards itself. Similarly, there are various other groups like NO2 group, like Cl group, CN cyanide group, fluoride. These groups have a strong affinity towards the electron pair. If they are present, they pull the electron pair towards themselves. So all electron releasing groups, because they release the electron pair, they loosen the bond pair, and therefore the electron pair is less strongly handed by these electron donating groups. The electron pair is less strongly held, and such electron group can be easily pushed to the excited state from ground state, and therefore we can say that presence of electron releasing group or electron donating group favors the phenomena of fluorescence. On the other hand, all electron withdrawing groups like Cl, Cn, NO2 group, they held the electron pair very strongly. They even pull the electron pair towards themselves, and therefore such a electron pair is tightly bound to these atoms or group, and therefore this electron pair does not excite easily, and we can say that presence of electron withdrawing group disfavor or presence of electron withdrawing group decreases the phenomena of fluorescence or discourage the phenomena of fluorescence. And in this particular case, because electron pair is tightly bound, we have to provide additional energy for the electron pair to get excited and then comes back to emit light radiation in the form of fluorescent light. So In general, these electron withdrawing groups, they do not let the electrons to get excited easily, and therefore these groups reduces the fluorescence intensity. So, if the bond strength is high, if the bond is stronger, the intensity of fluorescence is low. For example, there is a bond between two atoms, and the two bonded atoms A and B are connected with this bond. And if the intensity of this bond is very high, means the bond strength is very high, it is very difficult to promote these electrons from ground state to excited state, and therefore since more energy is required, if that energy is not available, fluorescence will not occur, or if it occurs, the intensity of the fluorescence will be low. So there will be lower intensity of fluorescence. Presence of atoms like oxygen or even metals, they reduces fluorescence as they promote intersystem crossing. I explained it to you yesterday as well, that for example, if oxygen is present, since oxygen attracts the electron pair towards itself, so it causes the electrons to be involved, and therefore it reduces the phenomena of fluorescence. It promotes intersystem crossing, and metals also promotes intersystem crossing. If we are doing analysis and we have an impression that our sample contains oxygen and metal ions, so for example, if we have prepared a sample, for example, this is a cuvette and I have prepared a sample over here in this room, and since air is present everywhere, this sample contains air as well, which has oxygen, and this oxygen is a very good quencher. It absorbs the electron pair, it attracts the electron pair towards itself, reducing the phenomena of fluorescence, and it promotes intersystem crossing. Means because of the presence of oxygen, electrons undergo flip and they changes from singlet excited state to triplet excited state, and when intersystem crossing is taking place, fluorescence will not happen. So we have to, in that case, I have to remove this oxygen from the sample. This can be done by passing nitrogen or argon gas. Since argon is a bit costly, we can pass nitrogen gas in this sample for some time, so that all the oxygen or all the air is removed and the empty space is filled with nitrogen gas. This is called as stripping. We can do a stripping by immersing pipe in this sample and passing nitrogen gas through that pipe, because we create bubbling through nitrogen gas, which pushes all the air to go outside this sample tube, and we have nitrogen only along with the sample, which does not cause this intersystem crossing. On the other hand, if metals are present, we can remove those metals by certain process. Means we can go for ion exchange. We can also do the removal of metals by precipitation. Means we can precipitate those metals by adding some chelating agents like EDTA could be added, ethylene diamine tetraesteric acid, that acts as a chelating agent, and that causes metal to get dormant, and the metal is trapped in the complex with chelate, and then it will not react and then it will not affect the electron pair, and it does not cause intersystem crossing. In this slide you can see that here we have fluorescence light being emitted from a sample. This is the sample of green fluorescence protein, which is shown to emit light of green color, but when oxygen is added, this green light is gone. But when oxygen is added, then this green light has gone, and the phenomena of fluorescence has been decreased, the intensity has been decreased, and instead of green light we get red light. Means if we are having this peak for our emission of fluorescence light, the peak will be shifted towards the right side. Means we will get even then means we are getting light radiation of even longer wavelength, and that is why the color that was earlier green, it becomes red, because red has a longer wavelength. This is because of the presence of cellular oxygen, because cells are using oxygen. Cell has oxygen, cells have oxygen uptake. That oxygen basically binds that fluorescence protein, and thus it reduces the intensity of the light. Means it decreases the intensity, it enhances the wavelength, and therefore instead of green light we are getting red light. So Increase O2 concentration causes decrease in fluorescence. So oxidized compounds have low fluorescence, and because of the paramagnetic property of this fluorescence, because of the paramagnetic property of this oxygen, because oxygen is paramagnetic, because oxygen is paramagnetic, because in oxygen gas if we have 8 at 16 electrons, so these electrons when we pair it on the basis of molecular orbital theory, 1s2 sigma 1s2 sigma star 1s2 sigma 2s2 and sigma star 2s2, at the end we place two electrons in two different orbitals, and these, because of the paramagnetic nature of oxygen, means these two electrons are placed in two different orbitals and they have a spin parallel, they have a parallel spin instead of paired spin, and since spin is parallel, so their total spin is plus half becomes 1, the multiplicity will be 3 in this particular case, means multiplicity will be 3 in this particular case, means they give rise to a triplet state, and therefore electrons moves to the, and therefore electrons show intersystem crossing rather than fluorescence. So this intersystem crossing occurs due to flip of spin because of the presence of oxygen, which has last two electrons placed in two different orbitals, as it is a paramagnetic species. So if we have high concentration of oxygen, it will decrease fluorescence intensity, so it will oxidize the compound as well, which decreases the intensity, and because of its paramagnetic property, which means it has unpaired electron, the last two electrons entered into different orbitals having parallel spin, and therefore oxygen favors intersystem crossing, means electron undergo flip and moves from singlet to triplet state rather than coming back and emitting light as fluorescence, because when electron changes its position from singlet to triplet, energy is lost as non-radiative deactivation. Then comes solvent viscosity also, just like we have electron donating substituent which increases fluorescence, or electron withdrawing substituent that decreases the intensity of fluorescence. Solvent viscosity plays a crucial role in the fluorescence or in the process of fluorescence, because if we have a solvent with very high viscosity, since in a highly viscous solution molecules cannot move easily, and if they move at slow speed, the speed of the molecule is slow, so they move at slow speed. Why? Due to high viscosity of the solution, and since molecule moves slowly, there will be collisions with low energy collision, because molecules are moving slowly, their kinetic energy is low, and if they have low kinetic energy, even when they collide, the impact is insignificant, and there will be no transfer of energy from excited species to a species in ground state, and there will be no reduction in the fluorescent, and there will be no reduction in the fluorescence intensity, because so a solution with high viscosity favors fluorescence because it reduces molecular collision. On the other hand, a solution with lower viscosity has more molecular collisions, and those collisions are taking place at high speed. So low viscosity decreases the intensity of fluorescence. So viscosity of the sample is directly proportional to fluorescence intensity. High viscosity has high intensity of fluorescence. Low viscosity has low intensity of fluorescence. Then comes the pi star transition. Since I explained you yesterday the types of transition, there are four types of transitions. There are, since I explained you yesterday the different types of transitions, there are three types of transitions: sigma, pi, n, pi star, and sigma star. And the transition that requires largest amount of energy is sigma star transition. Then we have n to sigma star transition, then in terms of energies comes the pi pi star transition, and then we have n to pi star transition. Sigma sigma star transition requires the largest amount of energy, and I explained you in the previous lectures that a light radiation with wavelength lesser than 250 nanometer or even lesser than 200 nanometers are very strong, means their energy is high, and this energy is high enough to cause breaking of the bond. So when these light radiation falls on a sample, they causes bond breaking, and therefore this phenomena is not observed. So specifically sigma sigma star transition does not show fluorescence. Even n to sigma star has low fluorescence probability. The fluorescence is mainly observed in case of pi to pi star transition and n to pi star transition. But in case of n to pi star transitions, these transitions occur when we have a double bond in the sample and a heteroatom. For example, in case of carbonyl compound, where carbon is attached to oxygen with a double bond, because of this double bond we have pi electrons here, and because of this heteroatom oxygen, it has two lone pair of electrons, so we have n electrons over here. So in this particular case we observed n to pi star transition, and the energy of n to pi star transition is very low. So when an n to pi star transition occur, very low amount of energy is absorbed. So rather promoting fluorescence, sometimes n to pi star transition restricts fluorescence because of their lower energy and promotes intersystem crossing. So just like the presence of oxygen, this is a paramagnetic species, or metal, if we have in our sample n to pi star transition taking place, because especially if we have, for example, oxygen present, as I just show you the example of carbonyl compound. So where we are having this n to pi star transition, since it requires lowest amount of energy among all the transitions possible, since it requires a lowest amount of energy among all the transitions possible, therefore the energy is not enough to cause fluorescence, and such transition rather support intersystem crossing. Again, this slide shows the relation between fluorescence intensity and concentration. Although I have already discussed about the effect of concentration on fluorescence intensity, but in this slide I am going to tell you the concentration range up to which the relation between fluorescence intensity and concentration is linear, means the concentration range till which the graph is a straight line, the graph is linear. So this is the equation. F is fluorescence intensity, then K is the proportionality constant, I naught is the incident light radiation, phi is the quantum yield, C is the concentration. Path length has not been placed in this equation because the point is to just explain you how the concentration range can be determined, because the point is to tell you that up to what concentration range the fluorescence intensity is directly related to the concentration. So the linear relationship between fluorescence intensity and concentration holds up to about 10 raised to power minus 5 to minus 6 molar concentration, means from 1 to 10 micromolar. At this particular level, the relation between F and C is linear. F is directly proportional to C. So if we plot a graph between fluorescence intensity and concentration, and if the concentration is in the range, for example, 2, 4, 6, 8, 10 micromolars, we will get a straight line. As we increase the concentration, the fluorescence intensity will increase correspondingly. But at higher concentration, this law will not holds good, and at higher concentrations, if we are going high, this equation will not holds good, and ultimately the graph becomes constant, and even at very high concentration the intensity of fluorescence decreases due to self quenching. So till this concentration of 10 raised to power minus 5 to minus 6 molar means 1 to 10 micromolar, the relation between F and C is linear. Now what happens at high concentration? What is actually happening at high concentration? Since we observed deviation at high concentration, then there must be some reason for this deviation. The reasons are given here. At high concentration, fluorescence intensity deviates from linearity. At low concentration, it is linear, but at high concentration, it moves from linearity, becomes constant, and at very high concentration, it decreases as well. There are three possible reasons. First is called as the inner filter effect. Inner filter effect. First is called as the inner filter effect. Inner filter effect refers to the absorption of the light of excitation. Inner filter effect refers to the absorption of light of excitation, and then the light that is emitted due to fluorescence, it is also absorbed. Means in this inner filter effect, since we have first of all absorption of light causing excitation, and when electrons come back, light is released, that the emitted light is again absorbed by the molecule. This is called as inner filter effect. Clear? So inner filter effect means the absorption of excitation light. Inner filter effect means the absorption of light for excitation, and when the electron comes back from the excited state to the ground state, the light that is being emitted, it is again absorbed by the same molecule. This is inner filter effect. And if that light is absorbed by some other molecule, it is called as reabsorption. This is the only difference. If this light that is being emitted, it is absorbed by the same molecule, it is inner filter. While if the light is absorbed by other molecules present in the sample, it is called reabsorption. Self-quenching means instead of, because of high concentration, there will be more collisions between the molecule, and those collision causes loss of energy or deactivation, which is a form of non-radiative energy loss. Therefore it is called as quenching, and since this quenching is taking place by the molecule of sample itself, it is called as self-quenching. So there are three reasons that causes reduction in the intensity of fluorescence light at high concentration. The first reason is because of the absorption of fluorescence light by the sample itself. Means the sample first of all absorb the light radiation for excitation. Electrons are excited. When those electrons comes back and they emit light as fluorescence light, as visible light, that light is again absorbed by the same sample. It is called as inner filter effect. Then there is a phenomena of self-quenching. In self-quenching, there are collisions between the sample molecules, and these collisions causes loss of energy, which is a sort of non-radiative deactivation, and in this way no light is emitted and fluorescence intensity decreases. And the third type is reabsorption, which means when the photons of light are emitted, when electrons comes back from excited state to ground state, those emitted photon of visible light, they are absorbed by other molecules that are present in the sample. These molecules absorb the light radiation, and in this way the fluorescence intensity decreases, and this is the third reason due to which deviation at high concentration are observed. Now the optimum concentration and practical implication. So if the concentration is very low, of course there will be very low number of molecule, because that the formula that I have shown you earlier shows that F is proportional to the intensity of light I naught or maybe P naught, and it is also proportional to C. Means if the concentration is very low, intensity will be low, but on the other hand, if the concentration is high, there will be some sort of collisions causing self-quenching or absorption of light by the same molecule, inner filter effect, or by other molecules of the sample, means reabsorption, that also decreases the intensity of fluorescence light. So we have to create, or we have to select an optimum concentration which is neither too low nor too high, and it should be moderate. It should be optimum to have an optimized fluorescence phenomena and to have high fluorescence intensity. Clear? So we have to select a concentration, or we have to determine that concentration which is neither too low nor too high, because both these too low and too concentrate because both these too low and too high concentrations have their own repercussions, decreasing the intensity of fluorescence. So it should be in between. So it should always be an optical concentration, a moderate value of the concentration, neither too low nor too high, because at too low concentration the phenomena will be hardly observed, because at too low concentration the phenomena of fluorescence would hardly observe, because there will be very less number of molecules to interact with the light, means less number of molecule to absorb that light, causing excitation of electron, while at high concentration there are various other effects causing deviation. So it should be optimal concentration. Beyond this range the deviation dominates in the form of reabsorption, inner filter effect, or quenching. And if we have high concentration, we have to dilute the sample to bring the concentration between the range. Even this happens in case of UV spectroscopy. If the samples are highly concentrated, if it also happens in case of UV spectroscopy, if the concentration is very high, the value of absorbance goes beyond 2, and if the value of absorbance goes beyond 2, it is out of range. Mean the formula A equals to epsilon B C does not holds good for absorbance values over 2, and therefore we dilute the sample. We may go up to 2 times dilution, or we may go up to 10 times dilution, determine the concentration, and then finally multiply it with the dilution factor to get the exact concentration. Clear? So we have to maintain the concentration at moderate value. If the concentration is very high, we have to make dilution of the sample to bring it in the optimal range. Then only we can calculate the concentration of sample. For higher concentration we have to dilute the sample so that our results will be reliable. Otherwise the linear relation does not holds good, and the concentration that we are going to determine, the quantitative analysis that we are going to do, is not correct. So this is about the various substituent groups and their effect on fluorescence, then solvent viscosity effect, and then finally the concentration range which is which must be, and then the concentration range which must be maintained, a moderate and then the concentration range which must be maintained to get a correct analysis done by using fluorescence spectroscopy. Thank you very much. In the next lecture we will discuss about the instrumentation of molecular fluorescence spectroscopy. Till then, take care.